basic question tells us that metabolic rate, the rate at which the body consumes energy, is important in studies of weight gain, dieting, and exercise. We have data on the lean body mass and resting metabolic rate of 12 women who are subjects in a study of dieting. Lean body mass given in kilograms is a person's weight leaving out all fat. Metabolic rate is measured in calories burned per 24 hours. The researchers believe that lean body mass is an important influence on metabolic rate. And then they give us some data on the mass and the rate of 12 women and ask us to sketch a scatter plot using a calculator. Here's just my rough sketch of the scatter plot. Here is a scatter plot on the calculator. The lean body mass is given in kilograms, and that is on the x-axis because it is this explanatory variable, as stated in the problem, that the researchers believe that lean body mass is an important influence on metabolic rate. The y-axis is the metabolic rate, which is the response variable. And part B asks us to describe the direction, form, and strength of the relationship. The scatter plot comparing the lean body mass to the metabolic rate of 12 women shows a positive direction. Since the pattern runs from the lower left to the upper right, the scatter plot displays a linear form since the point in the scatter plot are stretched out consistently in a straight form. The lean body mass and metabolic rate show a strong relationship since the points are relating close and follow the pattern. They're close. Okay, now on to the advanced question. And the advanced question gives us a table of data about the 6-minute walk test in children and adolescents. Boys completed a test that measures the distance that the subject can walk on a flat, hard surface in 6 minutes. For each age group shown in the table, the median distance walked by the boys in that age group is given. And here's the table that they give us. The X that we are going to be using is the midpoint of the age group, and this is the age group, and then the Y is the median 6-mile walk distance in meters. So A asks us to determine the least squares regression line and interpret the meaning of its slope. So I did this in my calculator, but I gave you a rough sketch of the dots and the line. So I've entered into list 1 my representative age, which is X, and into L2 the median 6 walk distance, which is in meters. And the question is asking us to determine the least squares regression line and interpret the meaning of its slope. So to figure out the regression line, you go to Stat, Calc, and then down to linear regression, and you press enter. And for A, you get 492.7977, and for B, 14.7633. And that's how I got my equation. Y hat equals 492.7977 plus 14.7633x. I interpreted the meaning of this slope by saying the slope can be interpreted as for every increase in the representative age, the distance walked in meters increases by 14.7633 meters. And this is the slope in the linear regression line. And basically what this is saying is for every time this increases by 1, these increase by 14.7633. So for the advanced question, part B, it's asking to compute the residuals and construct a residual plot. Determine if there are any unusual features in the residual plot as well as their meaning. What does it mean if there are no unusual features? So for part B, I took my calculator. I went list 3, second, stat, and 7. So it'd help if it was on. So in list 3, I'm going to hit second, stat, 7, which is resid, and hit enter. And that's going to give me my residual points. And to plot this, you're going to have to go to second, stat plot, and switch list 2 into list 3. And then hit zoom 9. And that's what the residual plot looks like. So finishing up part B, it asks us to determine if there are any unusual features. And looking at the residual plot, I said that the residual plot is not curved and the scale of the residual is rather small. There isn't a clear pattern in the residual, so the linear fit does work. There are no unusual features in the residual plot, which means that the predicted y value and the observed y value are relatively close. There are no outliers or influential points, as well as the data is random, so there is no sign of deviation from pattern of the least squares regression line. What residuals tell us is the distance that the points are from the least squares regression line, so they're all relatively close. And last but not least, we have the AP question, which states, commercial airlines need to know the operating cost per hour of flight for each plane in their fleet. In a study of relationship between operating cost per hour and number of passenger seats, investigators computed the regression of operating costs per hour on the number of passenger seats. The 12 sample aircraft used in the study included planes with as few as 216 passenger seats and planes with as many as 410 passenger seats. Operating costs per hour range between $3,600 and $7,800. Some computer output from regression analysis of these data is shown below. Here is a graph that I sketched from the one that they gave us. Here's the information that it gave us. It gave us a predictor and a coefficient for the constant and the seats. And for the constant it was 1,136, and for seats it was 0.673. And part A asks, what is the equation of the least squares regression line that describes the relationship between operating cost per hour and number of passenger seats in the plane? Define any variables used in this equation. So they give us these two coefficients, and this would be A and this would be B. So my least squares regression line turned out to be y hat equals 1,136 plus 14.673x. And A is 1,136, which is the constant for the operating cost per hour. And B is here, and that is 14.673. And it represents the number of seats. It's also the slope, so it's representative of the number of seats that increase for every increase in operating costs, and you can see that in the scatter plot. So for every time this increases by 14.673. Part B of the AP question asks, what is the value of the correlation coefficient for operating costs per hour and number of passenger seats in the plane? Interpret this correlation. So the correlation coefficient is R, and they give us R squared here, which is 57%. What I did was take 57% and square root it to get R, which is 0.0755. And since the R value is close to 0, it indicates a weak linear relationship. The linear relationship increases as R approaches 1 and moves away from 0. Since 0.0755 is closer to 0 than it is to 1, it indicates that it is weak. Indicates the points in the scatter plot lie in a relatively straight line as well. So if it were closer to 1, it would indicate that the points were straight. And as you can see from this, they are not relatively straight, they're in clusters. Since the R value is closer to 0, it indicates a weak linear relationship and the lines are not in a straight line. The R value indicates a weak correlation since it's not resistant. Part C of the AP question asks, suppose that you want to describe the relationship between operating costs per hour and number of passenger seats in the plane for planes only in the range of 250 to 350 seats. Does the line show in the scatter plot still provide the best description of the relationship for data in this range? Why or why not? So basically what this question is asking is if we were to decrease the range of these plots from just 250 to 350, would this line still describe the data? And what I said is no. The line shown in the scatter plot will not provide the best description of the relationship with the range 250 to 350 seats. If you remove 5 points from the scatter plot, the least squares regression line will not describe the observations due to potential outliers and influential observations. The current least square regression line is being pulled towards them and to the specific shape of points. The points from 200 to 250 and 350 to 400 range are potential influential observations or outliers and are the reason for the drastic change in the line. So since these points are potential outliers or influential observations, if you take them away, that line does not describe those data points at all. And that shows that they are influential or outliers because if you take them away, the line changes drastically. And that is it. Adieu.